Yeah, so basically, there may be a bunch of other nodes in this graph, a whole bunch of other cities.
Right.
So
Right.
the MST, which gives you the minimum tree for this entire graph, how do we know that
Right.
that's going to be the one that's optimal for finding S2T?
Because that's how MST works. MST is going to get the minimum edges. Now, if you were to say that, okay, well, what if I had a even smaller edge from S to T? What's going to happen is that by adding that edge into the MST, you would create a cycle. And then you would go ahead and remove the largest edge of that cycle. And if that smaller edge that you've added to the MST is smaller than any of the other edges in the cycle, and then we can replace that edge, the larger edge, with a smaller edge, we would in fact have lowered our overall weight of our MST. And therefore, the thing that you claimed was an MST actually wasn't an MST. And that's a proof of like why something, when you have an MST, it always has to have all the minimum edges that would give us that tree. Now you could have like if your edges are if you have duplicate of the edges, like if the edges aren't distinct, your MST could choose a one edge over another that has the same weight, but that would still give you like the same capacity solution.
Got
Does
it.
that make
Thank you.
sense?
Yep.
Any other questions? Right, cool. And this wasn't presented to you as an MST problem. When we get to the next chapter, which is chapter 5, when we actually talk about more MSTs, you'll start to see like the properties of MST that you should really be like careful about and concerned with. This is just sort of like a preview of MSTs because I didn't like the Dijkstra solution that the book was pushing you towards, because it kind of like conflicted with what this class is asking you to do.
I have a more straightforward solution, but it's not as optimal as yours. That is, you can use the algorithm designed in part A, the non-modified version, just run it along with the binary search. You first sort all the edges, and then you start with the middle one. If you cannot find a parse with the capacity this much, then you go to the right. Otherwise, you go to the left.
So you sort all the edges. Wait, are we answering part A or part B?
Part B.
So you sort all the edges, and then
take the middle one, and remove all the edges with capacity greater than that number. Try to see if you can find a path from S to T in linear time. So if you can, then you go to the left array. If you cannot, you go to the right array.
Okay, so then, okay, so what's our runtime? Let's see.
So it's log m times the running time, the linear time for each algorithm. It's the same as Dijkstra's.
So running explore is O of n plus m, and you do that across all edges, which is O of doing a binary search. So it's O log m, and so that gives you O of n plus m. Log m becomes
log n.
Log n. So Yeah. So you are looking for the exact point in your
Exactly. In my sorted list
your
of
binary
the
search
capacity.
on when the capacity goes from feasible to unfeasible.
Exactly.
I think that works.
Thank you. And another question, when I see you write the algorithm, you always use explore. Can I say breadth first search or depth first search from a starting node? Must I use the explore?
Wait, so Dijkstra, or you mean BFS or Dijkstra's?
I mean BFS, DFS.
You can't, well, there's a post on why you can't just run DFS without giving additional details. So avoid that. You can use BFS if you want. You would have to say run BFS and decide if from BFS from S and decide if T is infinite or not to determine whether you can reach it or not. I use Explore because Explore is very single focused. It does one thing. It does it in a very understandable way. So I just like to use Explore.
Why cannot we use DFS?
Well, how would you, if you use DFS from S, how do you know if it can reach T or not? What's the actual steps to do that? Because Explore gives you back a visitor array and it'll tell you whether T is visited or not. So like it's part of your output. But what does DFS give you that you would
maybe I keep the distance array, which is initialized to be infinite. If I finish running DFS,
right, so that's right. So yeah, you could do that with BFS. Yeah, but if you use DFS, what would you use as your output to determine that?
I need to keep an array of visited.
But your array of visited in DFS is always going to be true, because what happens is that after a single run of Explore, if there's any unvisited vertices, it's going to go read that array, determine what to run Explore from next, and then it'll fill in that array with more visited vertices, and then it's going to keep doing it until the entire array is true. So that array, when it comes back to you after a DFS run, is all true. It doesn't give you any information that you would need. Right. That's why, like, if you haven't read that post yet on the difference between DFS and Explore in this class and why we use one or the other, I would suggest going over it.
Okay, thank you.
Yep. All right. So that is.
I have a follow up on the alternative using the modified binary search. The edge list is not sorted. If we sort them, don't we need to account the runtime?
Yeah, but I mean the runtime is O of M log, and that gets eaten up by this overall runtime at the bottom. I was just trying to figure out if the binary search times lock-in is correct. I mean Dijkstra also has to do the sort, right? That's why it has that lock-in.
Okay, thank you.
Yep. Yeah, like the sorting would be O of M log M, right? And it gets eaten up by the runtime of the rest of the algorithm. Like I wasn't trying to like write an official runtime / solution to this. I was just trying to play it out in my head to see if that would actually work, and I think it does.
Got it. Thank you.
All right, and you guys said that you have a solution to 4.14.
Yes.
All right, do you have a solution to 4.20?
No, if you want to skip it, you can.
Oh, okay. All right, does anybody want to see 4.2 or should I just skip it? Oh, someone said wait. What am I waiting for? Wait,
There you
4.2
go.
is Is it homework 6?
Yes.
What?
Yes.
Why did someone? Okay.
It's not
is.
quite the same thing because it's undirected edges rather than directed, but it's very similar.
And then we give 4.2 as a practice.
Yes.
Okay. That's not good. And we did not give a solution though. So that's, oh man. Okay. I'm gonna skip 4.20, and I will raise that as a concern with other TAs. When was it listed as a practice problem?
This is given by Dr. Brittle.
Okay. All right.
It's one of his favorite.
I was gonna go over it because it is actually a fun problem, but since you have it for your homework, I think that's fine. Did you get a solution to 4.21?
No.
Okay. All right, I'll go over 4.21 real quick. This is again one of those ones that's like is sort of like a in between of dynamic programming and graph problems. So I'll just go over the solution real quick. But in other semesters, we typically cover this in the dynamic programming part of the class. And then after this one, we'll take another break because that's the end of this chapter. All right, 4.21. Shortest path algorithms can be applied in currency trading. Let C1, C2, ... Cn be various currencies. For instance, C1 might be dollars, C2 might be pounds, and C3 might be lyre. For any two currencies, CI and CJ, there is an exchange rate. This means that you can purchase some rate of units in currency and exchange it for 1 unit of dollar. These exchange rates satisfy the condition that R of ij times R of ji is less than 1. So that if you start with a unit of currency CI, change it into a currency CJ, and then convert back to the currency, you end up with less than 1 unit of currency. The difference is the cost of the transaction. Given an efficient algorithm for the following problem, given a set of exchange rates R of ij and two currencies S and T, find the most advantageous sequence of currency exchanges for converting currency S into T. Toward the goal, you should represent the currencies and rates by a graph. Okay. What's kind of cool about this is that my team at work actually recently someone is working on something to do with currency. I work on backends for Google Travel. And so one of the things that airlines care about is the currencies of the thing that they are selling. So if they're selling you a flight or they are selling you baggage, carry-on, extra legroom, stuff like that, they care about currencies. And so we need the currency rates to be sort of streamed to us by some organization that deals with currencies. And then we have to like convert them and do all these special things. So this is like a very real thing that like that you do in real life and do work. So let's see my solution to A. Okay. But like these type of things is like so well controlled by some like agency that looks over this that you're not gonna find a way to like manipulate currency to like go around to make this like massive amount of money. I think there's actually like systems in place that short circuit anything like this. Like if they start seeing like a trading currency like spike or skyrocket, they immediately like put a halt to it and then take a look at like why this is happening. So you're not going to get don't bother trying to find a way to like make millions of dollars of doing this. And currencies as a rate actually goes into far more decimals than you see, because you do work with like fractions of a cent and stuff like that. So that's also kind of cool. All right, so we need to convert the multiplication of exchange rates to the addition of weights. We can achieve this by using logarithmic, since log of x times y is equal to log of x times log of y. So for all rates, ij in our exchange rates, if we take this weight and we change it to the negative log of r of ij, we can pass. Yeah, so we convert this rate into a log, and now we can add it. And because we can add it, we can put it all into Bellman-Ford to do a shortest path based on addition instead of multiplication. So this is how we convert it into a Bellman-Ford black box use. I think when I had this problem, I think it might have been the homework problem. This clue actually had to be given to me. Like, I don't think I would have came up with this on my own at all. Like, to know, like, I knew that we were looking for a shortest path solution, but I don't think I would have came up with the fact that like if I manipulated the rates into a log, then I can do addition with them. So that's that. And then the correctness I will give. All right. So this works because Bellman-Ford gives us the shortest path from S to any t. The shortest path gives the most advantageous sequence of currency exchanges for converting currency S into currency t. If there's a negative cycle in the graph, this may not be the correct answer, and we will look for this in part B. However, we can also look at the path t and see if any vertices are repeated. So if there are any vertices are repeated, then you know that there was a cycle, or a negative cycle more specifically. And notice how we have to use Bellman-Ford and not Dijkstra's because because some of these rates going from one to the other can be negative. So like you could start off with a currency that gives you less of a second currency. So you have to consider negatives. And so you can't just use Dijkstra's. Okay. And so that's how we solve part A. Any questions about part A before we move on to part B? All right. Oh, and yeah, the runtime is to convert all the rates takes all of M, assuming those are all edges in our graph, and then running Bellman-Ford is all of n times M, and so the overall runtime is all n times M. Okay, and then part B, we are going to, oops. Part B doesn't specify which two currencies we're going to get from and to. We're just looking for any opportunity to make some extra money. Part B asks, Oh, I didn't actually read. All right. The exchange rates are updated frequently, reflecting the demand and supply of the various currencies. And this actually does get updated pretty frequently. I think throughout the day, we get data several times per hour. Like it's not like this like constant stream, but like there is like a regular cadence on these exchange rates getting converted. I think. Yeah. So the way you get the rate is actually not from one rate to the other, and this is actually why these negative cycles don't happen in the currency conversion. We use what's called a neutral unit of construction, or a nuke, and is defined as the neutral unit of construction or neutral unit of currency is a private currency used by the airline industry to record fare calculation information. Set of exchange rates is issued by the International Air Transport Association every month. So there's a consolidation of the exchange rates, and then there's a regular update throughout the day of what these exchange rates are. I don't know if you care about this information. I always thought it was kind of interesting when I learned about it. So anyways, updated frequently, supply of various currencies. Occasionally, the exchange rates satisfy the following property. There's a sequence of currencies, C1 ... to C of IK, such that the rates are greater than 1. This means that by starting with a unit of currency C of I, and then successfully converting it to currencies all the way to C of IK, and finally back to C of I, you would end up with more than 1 unit of currency. Such anomalies last only a fraction of a minute on the currency exchange, but to provide an opportunity for risk-free profits. So solution to part B would then be the anomaly can be reduced to if a negative cycle exists for C of I. So for any currency, if a negative cycle indicates we can improve the path cost with each cycle. So we pass into Floyd-Warshall algorithm our currency table, our weights as computed in part A, and then we get back this P, which tells us what the shortest path is from U to B. Step 2, if P of II, which is the path of a vertex to itself, is less than 0, which means that there has been a negative cycle detected for any currency, then there exists a negative cycle, and a negative cycle indicates the presence of such an anomaly. Our algorithm returns true if a negative cycle exists. And the reason this works is because it's just the truth of how Floyd-Warshall works, it returns a negative cycle cost for a vertex to itself, if and only if the vertex has a negative cycle to itself. And so the runtime, again, is we convert all the rates to logs, which takes O of M, Floyd-Warshall is O of N cubed, checking all distances of vertices to itself is O of N, and so your final runtime is O of N cubed. All right. Any questions about this? We good? All right. We're gonna take a break until 5:30. That's about 4 minutes. I'll see you guys then. All right. Five. Oh, my mic on? Can everybody hear me okay?
Yes.
All right, great. All right. Chapter 5. I actually really enjoy MSC problems. They might be my favorite graph problems. There's just something about MSC problems that's like, it's a little bit like, there's some simplicity to it on like how that graph looks when you're done that like just makes it easier for me to digest. Oh, and one suggestion that I have on doing these. I know I haven't been doing them because I've been just sort of sharing my my solutions directly. Draw a graph, right? Like you have paper, pencil. Draw a graph to sort of like represent what you're trying to do, and draw some what's called like a toy graph, like like a simple graph of like what would happen if I had like this type of graph. What does your algorithm do? What does your algorithm do if I have like this type of graph? And what does your algorithm do if I have like this type of graph? And then what happens if I have like random islands or like a disconnected graph? Like just draw these simple graphs as you're working with your algorithm to get an idea of like how it would work and if it does work at all. Oftentimes you'll think you see like a simple solution and then you start it and then you find out that like it's a contradiction. So like when someone asked me like, can't you just do like what happens if you have a single sink or a single source, right? And I was just like, well, if I had a graph like this, right, that immediately breaks that solution. So don't, these are like a super complicated graph is like, ooh, yeah, this is like, good reading material. But when you're doing the exam, simple graphs are good for like just checking to make sure you haven't broken anything. So that is my advice on doing graph problems. Pretty sure when I was trying to solve these problems, I drew a bunch of graphs. I still kind of do when I'm solving new problems I haven't seen before. All right, let's see. First problem is 5.5. Okay, so this one just sort of like asking you on understanding MSD. So I'm just gonna kind of post the answer and then maybe draw some graphs to sort of talk about this. All right. Consider undirected graph G with non-negative edge weights. Okay. WE greater than or equal to 0. Okay. Suppose that you have computed a minimum spanning tree of G and that you have also computed shortest path to all the nodes from a particular node S. Now suppose each edge weight is increased by 1. The new weights W prime equals WE plus 1. Does the minimum spanning tree change? Give an example where it changes or prove it cannot change. So it doesn't. Since all edges increase by 1, the sorting of the edges does not change, and the lightest edge across a cut that does not create a cycle will remain the same at each step of an MST algorithm, right? So because, like I said, this is there's a big difference between shortest path and MSTs. Because MST selections of your edges are independently, they are compared to each other, but you are a greedy algorithm that you are picking one edge at a time. If all the edges are modified in the same way, it doesn't change their ranking or way they are in the sort from each other. And so the same edges that could make up a MST would still be those edges. It does not change. So it does not change the fact that your initial MST is still MST if these edge weights are changed in exactly the same way. Okay. Is this a quiz question? Really? Well, I've answered it. I don't know. Like I think on the semesters where I am actually like participating in the class, I do a better job of keeping track of like what's assigned and what's not. But I feel like, I mean, if it's a practice problem, you're allowed to discuss it in class, right? Like it is not your fault if we accidentally assign a practice problem that you're allowed to discuss. All right. All right, second part. Do the shortest path change? Give an example where they change or prove they cannot change. So we already did this, right? We did this with the dice rest question earlier, right? So suppose the shortest path from S to U is over X edges with a weight of 1. If there exists E equals SU with a weight of X plus 1, then if we increase all edges by 1, the previous shortest path from S to U is now 2 times X, while E of S to U is X plus 2. So for some X, X plus 2 is less than 2X is true, and therefore the shortest path would change. Okay. Any questions about this particular problem? Okay. If nobody has questions, I will move on to the next problem. All right, 5.6, unique MST. Someone asked, does the path distance get changed, or is it the actual path? And the actual path can change. That's what I'm saying. So like, right. So right now, your shortest path, right, is going to be over right here, right? It's going to be 1, 2, right? Let's make this a little bit more clear. Trying to pick numbers where it is. Okay. Hold on. All right. So your current shortest path is going to be right here, right? That gives you a total of 3, right? If we were to add 1 to each of these vertices, right, this becomes 2, this becomes 2, this becomes 2. So now this becomes 6. But if we were to add 1 to this, this becomes 5. So now you've changed your shortest path, right, to become this instead, because 5 is less than 6, right? So by adding 1 to every single edge, you can effectively change what the shortest path would be. Not just the actual weight of the path, but the actual path itself. Okay?
I have a question on edge weight and edge length. Do we use that interchangeably? When we're
Yes,
dealing.
it is. Length and weight is the same thing.
Okay.
Hmm. All right. The next problem is 5.6. Okay. Unique MST. So let G equals VE be an undirected graph. Prove that if all its edges weights are distinct, then it has a unique minimum spanning tree. So what's nice about this is that it's actually, it tells you that it's true, that you can assume that it's true, because otherwise it would ask you to see if there's a contradiction to it. Someone brought a good point. Sometimes weight can be negative, which is true, but length is always positive. I think like in practice, that's pretty much true. If we give you like, the weight of something or the length of something, we'll give you enough details to like sort of like figure it out. I think weight is like technically the correct terms. I think like length tends to be used in like in more real world problems, like what is the length of this highway, which is effectively your weight. But because highways can't be negative, like length makes more sense. The two words are used interchangeably, but length is probably used more more practically with something that's like concrete and has some like meaning behind the word length, if that helps. Yeah. And that's correct. Like Tim is saying, that if there's a positive constraint to the weight of a graph, we would tell you. Don't just read length and be like, oh, that automatically means that it is positive. But I will say that if you read about the length of a highway, right, you should assume that length of the highway is positive, because it would make no sense to be negative. So, like, I don't think I would be very happy if we gave you a problem that like bent your understanding of physical properties of the world. That would be not cool. All right, unique MST. Okay, let me give my solution. Basically, we're going to prove this by contradiction. Like, let's find a way to contradict what the statement is saying. And if we can't find a contradiction, then it has to be true, right? So suppose we have a T1 and T2 as two different MSTs of G, right? Let's suppose that they're not distinct. What happens if we have two T1 and T2 as two different MSTs of G? An edge in E1, edge E1, which is in T1 and not in T2, therefore can be added to T2 and create a cycle, right? Because the definition of a tree is that you only have edges such that adding any more edge within that graph creates a cycle. So any edge that's in one MST and not in the other MST, when you add it to that MST would create a cycle, right? So an edge E2 in this cycle, let's say, another edge that has been created that is part of this cycle exists in T2 already and not in T1 because it would create a cycle in T1 because we know that T1 is supposedly an MST. There can be no cycles in it. So now with these statements out of the way, we can compare E1 to E2. E1 cannot be the same weight as E2 because all weights are distinct. That's part of what this problem statement is. So if E1 is less than E2, then T2 can replace E2 with E1 and get a smaller weight. Therefore, T2 cannot be an MST, right? If you could have replaced one of the edges in T2 with a smaller edge, then T2 was not an MST, okay? Conversely, if E1 is greater than E2, then T1 can replace E1 with E2 and get a smaller weight. So then T1 cannot be an MST, right? So because of all these conditions and then how they contradict each other, there cannot be two separate MSTs to G if all weights are distinct, and therefore G must have a single unique MST. Okay? Any questions about this proof? No? Good to have an understanding of this. 5.7. 5.7 is a fun one, interesting one. This is what some students had asked, like, what happens if we flip or invert the edge weights? What happens is that you get a maximum spanning tree if you run this MST algorithm. So show how to find the maximum spanning tree of a graph, that is the spanning tree of largest total weight. All right, so we're going to create a new set of weights such that W prime is equal to the negation of all the weights in W. So that is every weight in W is multiplied by -1 to get weights, get a weight in W prime. We call Kruskal's MST algorithm with this graph and these updated weights, and we get back a edge that is the maximum spanning tree, such that E max ST are the edges for both the minimum spanning tree of G W prime and the maximum spanning tree of G and the original W. Okay, that's what it means. It means that if I was to get the spanning tree of these negated weights, if I get the minimum spanning tree of these negative weights, it is effectively the maximum spanning tree of the original weights. And so we return this as the maximum spanning tree of G. And so the reason this works is that by negating all the weights in G, we have inverted the weights of edges in G such that the lightest edge are now the heaviest edge, and the heaviest edge are not the lightest edge. By running Kruskal's, we get the minimum spanning tree, which is actually the maximum spanning tree of G. You saw when I, illustration of like, if we do -1, 1, 2, 3, right? If we then take the negatives of this, we get 1, -1, -2, -3. And it just basically reverses the sort of this, whereas -1 was the minimum, it is now the maximum, or whereas 3 was the maximum, it is now the minimum. And so when you go do a minimum spanning tree of this, what's going to happen is that it's going to pick this -3, which corresponds to this 3. Then it's going to pick this -2, which converts to this 2. And so it's going to go from the largest weights first down to the smallest weights. And so every time it picks something, it's going to try to maximize its weight. So negating the edge weights takes all of m, running Kruskal's is all of m log n, and so your final runtime is all of m log n. Cool. Any questions?
The negating the weight can this is only applicable to MST, right?
This is applicable to doing this to get a maximum spanning tree. You can mess with the individual weights of a graph when you're working with MSTs or some sort of spanning tree because of the property that MST algorithms care about the edges in comparison to each other where it is on when you sort it, and messing with the weights either by adding the same number does not change your sort, or negating them reverses the sort.
And this does not apply on shortest distance because that's when we consider the entire path.
Yeah, because path is a summation, right? It's not the individual edge does not give you enough information on the path. It is the summation of those edges. And therefore, whatever changes you make to that edge grows based on how many edges is in that path. And if a shorter path is less edges or more edges, it disproportionately changes the distance of that path. And so it doesn't it messes it up more so than a MSD problem would.
Okay, that makes sense. Thank you.
Cool. All right, that was 5.7. 5.9 has a whole bunch of questions, which now I'm somewhat scared to present because some of these might be quiz questions. So I'm going to skip 5.9. I'm sorry. 5.2 is the feedback. Oh, this is actually a very good follow-up to the 5.7 problem because it's actually very, very related. All right. A feedback edge set of an undirected graph is a subset of edges such that intersects every cycle of the graph. Thus, removing the edges E will render the graph acyclic. Give an efficient algorithm for the following problem. An undirected graph is your input with positive edge weights, right? A feedback edge of minimum total weight. Cool. I will say that what's interesting about this problem is that when I got this as a homework, was it homework? Yeah, I got this as a homework. This part right here was left out. And leaving out that these are positive edge weights makes this problem more difficult and more harder to explain. I'm going to solve this problem as is without the positive edge weights. I think it'd be interesting for you guys to consider what happens when the edge weights are not always positive. This is 5.20. Let me go ahead and put the there. All right. So I know this is kind of confusing, but the way to read this is right. What a feedback edge set is that if you remove all the edges of E prime, it will render the graph acyclic, which also means that if you add an edge from the feedback edge set into the graph, such that intersects every cycle. Wait, let me take that back. That's not true. So your minimum feedback edge set is going to be all the edges that would cause a cycle if you added it back to the MST. Okay, so that's like if you had a graph that was like this, and this is 1, 2, 3, 1, 3, 2. Okay, your what is it? Is it minimum? Yeah, minimum total weight. Yeah, so if your minimum total weight, what you would want to take away from this is to remove the edge such that this is no longer a cycle. You would take this one away, right? Because you want to take the minimum edges away. Okay. What's interesting about that is that leaves you with a maximum spanning tree, right? Of this cycle, if we were to keep 2, 3, and 4 and take away 1, that's actually our maximum spanning tree. So that should clue you in that the feedback edge set is the set that you take away to get a maximum spanning tree. Okay. Right. Is there a disagreement of whether this is 5.2 or 5.21? Is this 5.21?
.20 for the PDF.
Okay. Some students think it's 5.21.
I'm a little bit confused about the term intersect average cycle. Could you please draw another example? Because this seems to me that the edge, it lies on the cycle. It's not intersect with the cycle.
That's what it means. Like it's like a weird term that like if it intercepts a cycle, it means it's on the cycle, part of the cycle.
Can you draw another example? Not so trivial one. Intersect average cycle in the graph. That is a little bit hard to imagine.
Okay, so well, it's not a single edge; it's a subset of edges. If that's what you mean, like if I had,
but in your example, you only have one cycle, right? Okay.
If I had this, right? So I have, how many cycles do I have? I don't know how many cycles I have, but if I was to take out, if I was to say this edge and
but based on your terminology, intersect means on the cycle, then the top edge is only on 2 cycles. It is only intersect 2 cycles, not the left one, the right one, right?
Right. That's what I was trying to say, that it is a subset of edges that intersects every cycle. The collection of your subset of edges intersects or is on every cycle. It's not that a single edge is connected to every cycle. It is the subset. So if we say that I take these 3 edges, I will have handled the top, the left, and the right cycles.
And the middle one.
So this and the middle one. So these 3 edges would be a feedback edge set. So if they were all were to be deleted, so if we deleted this, I would still have a cycle. If I deleted this, I would still have a cycle. If I deleted this,
you still have a cycle.
Okay, so one more then. Let's go with this one. So if I delete that one, right, those are my feedback edge sets. Now I have no cycles. So those are my 4. So any number of edges can be deleted to sort of achieve this, but we want to get the minimal. We want to remove the lightest edges out of this to get our minimum feedback edge set. Okay. So let us present a solution to 5.2. Familiar. Because what we're going to do first is find the maximum spanning tree. So we're going to do the exact same steps. We're going to get our max spanning tree. And then what we're going to do that's not part of our maximum spanning tree. So this part came from the previous problem, and then this is the additional step right here. We're going to take our E minus maximum spanning tree, and we're going to get our feedback edge set. That is, we get all edges in E that are not part of the maximum spanning tree. Okay, and then we return this as our minimum weight feedback edge set. So the way this works is that we first create a maximum spanning tree by negating W so that maximum edges are now minimum. Running crisscross then gives us the maximum spanning tree. We already talked about this. A spanning tree is defined as a set of edges in G such that all vertices are connected without any cycles. Therefore, any cycle in G must have at least one edge removed from the for any cycle in G must have at least one edge removed to remove the cycle. So any edge in E without the spanning tree must therefore be an edge that would create a cycle when added to back. So this is a feedback edge by definition. The feedback edge set derived from the maximum spanning tree will be the minimum edge, minimum weight feedback edge set, because the minimum weight edge cycle is always left out of the maximum spanning tree. So this is just the inverse. If you say that the heaviest edge is always left out of the MST, then the lightest edge of a cycle is left out of a maximum spanning tree. And so by doing that, we get the minimum feedback edge set. And so negating edge weights all of M, run cross skulls, all of M log N, calculate this minimum edge feedback edge set is all of N plus M. And so your overall runtime is all of M log N. Any questions?
So using the weight negation to find the maximum spanning tree and then justify that the minimum weight of the edge of the circle will not be part of the maximum weight of MST. We basically using the cycle property that for a
you're
minimum.
You're using the cycle property, but you're flipping it around because the cycle property generally says the heaviest edge of a cycle cannot be powered of an MST. The flip
Correct.
of that is that the minimum edge of a cycle cannot be part of a maximum spanning tree.
Okay, so
Okay,
that's
so
why
that
we
becomes
need
your-
to. That's why we need to
and that
know
effectively
the
becomes-
cycle property.
Yeah. Yep.
Okay.
Okay. Yes, very good, Clint. That is exactly why it's a much different problem if it is a positive edge weight. So Clint says, for correctness, I think the fact that the edge weights are positive is important since it means we don't want to delete any more edges than we need to be left with a tree. Like if the edge weights could be negative, we might also want to delete edges beyond just what we need to limit all cycles. And that is correct. Your feedback edge set, right, doesn't have to be just the edges that create a cycle. It could be more. The definition is that all edges in the feedback edge set is enough to intersect all cycles. But you could certainly add more more edges to the feedback edge set, and it could, you could grow that to be basically every edge if you needed to. But in order to do a minimum for all positive edge weights, You just want the fewest edges in there because adding an edge is always going to make that number go up as long as the edge weights are positive. However, if those edge weights can be negative, then you actually can lower the total weight of your feedback edge set by adding those negative edges into your feedback edge set. So if this was not stating that it only has positive edge weights, you actually want to add all your negative edges in there as well. Yep.
So if this does not specify the edge weights are positive, do we still use the same approach that negate the?
The only thing you would change is that you also add all the negative edges. So let's say this is -3, and this is -4. So your lowest, your minimum edge on this cycle would be the -4, right? So you would want to take this edge, okay? But if you took this edge with you as well, you still don't have a cycle, but your -7 is now a lower number than your -4. So you actually want to grab both of these edges. So you want to grab all the negative numbers on top of any possible minimum edges.
Do we add the negative edge after we found what's being eliminated, or we?
Yeah, you add all the negative edges on top of that as well.
I think both orders are okay. You can either first take all the negative edges away and check if the remaining graph has a cycle. If it does not have a cycle, it stop. If it has a cycle, you keep using this algorithm to remove more positive edges.
Well, unfortunately, doing it from the cycle point of view is actually kind of slow. So what you want to do is just take the non-maximum spanning tree edges first, because you have to take those. You have to take those to not have any cycles, and then add the negatives.
I think.
Or I guess that's yeah. That's so what you can also do is first take all the negative edges.
You get a smaller graph, right? Then you work on the smaller graph.
Yeah, but then you get a disconnected graph. You could potentially get a disconnected graph, and that has all sorts of weird things with spanning trees. So it's better to just get the maximum spanning tree, take all the edges that are not in the maximum spanning tree, and then add to it all the negative edges. Otherwise, you may not have proper graph.
But the program itself does not assume it is a connected graph, right? At first, so you may start with a disconnected graph already. Unless you say it's a MST or maximum ST problem, so it must be connected.
Kruskals could work like that because Kruskals goes through every edge and considers it. Prims would fail because if you pick a vertex that's disconnected in prims and you're supposed to continue adding the closest vertex to the subtree that you have, it'll just stop, right? There's no more. It'll consider that there's no more vertices, and then you wouldn't get the edges on the other part of the forest. It's called a forest when you have a bunch of trees. So prims would not work. Kruskals might, but that's like added confusion. I would just get the maximum spanning tree to begin with, and then go from there. Does that make sense? If it doesn't, it's okay. Like this part's like, I think at this point above and beyond what you need to really understand.
Yes, thank you.
Okay, cool. 5.22, then 5.23, and then we take a break. 5.22. I just did. Wait, hold on. What am I looking at? 5.22 update MST. Is this going to get me in trouble for the quiz? This looks like the type of thing that might have quiz problems in it. Let me see. Okay, I think this one's fair. I'm going to answer it. That looks okay to me. All right, you are given a graph G with positive edge weights, yay, and a minimum spinning tree T with respect to these weights. You may assume G and T are given as adjacency lists. Now suppose the weight of the particular edge E is modified from WE to W cap E. You wish to quickly update the minimum spinning tree T to reflect this age without recomputing the entire tree from scratch. There are 4 cases, and each case give a linear time algorithm for updating the tree. So this is nice because I've told you, right? Like if you are given a MST already and we update one or a few of the edges and you go, you know what, I'm just going to run Kruskal's and Prems all over again. That's not great. That's going to give you lots of negative points. So you can actually update it much more quickly, having assumed the rest of the MST is done. Okay. So I'm going to give the solution to all 4 parts, and then I will walk you through some of them. All right. So in part A, E is not part of E prime. What the heck is E prime? Oh, so a given edge is not part of the MST, and we've made that edge, we've increased that edge, right? So adding weight to an edge that is already not part of the MST is not going to make it magically be needed for the MST, right? All it does is make it even, less of a candidate to be part of the proper MST, right? That should make sense, I hope. So no update needs to be changed. You just say, yeah, this edge that wasn't small enough to be part of my MST just got bigger. So now it still can't be part of my MST. Now, what if E was already was not part of my MST, but its weight has decreased? Okay, so the algorithm we can do is let E is equal to UV, run explore on T from U, find the heaviest edge along the path from U to V using the previous array, because we know, like I said, right, we know that there's only one path because MSTs are acyclic, and so there can only be one path from U to V. So now using the previous array, we can check what the heaviest edge is. And if the heaviest edge along this path is now heavier than our updated edge, then we can remove it and add into it E to create the new MST or update MST. This takes all of n plus m to check for the heaviest edge explore takes O of n plus m, and checking for the heaviest edge takes O of n. So what this means is like if I had right, let this be a cycle, right? And if I was to update this MST, if I was to turn this to MST, I would remove this edge, right? And this is now my MST. And this is true for like all the different cycles that's like in the graph, right? Is this stop? This okay. This is true for any of the cycles, right? Now, if I updated this edge that I'll leave off right here to, let's say, 2, right? This edge would connect here and here. So I run a DFS, or sorry, explore from here to get my path from here to here to here. And I look for the heaviest edge along this path. This heaviest edge is 3. Edge. And we add this to our MST. Our MST has now gone down by 1 simply by removing the other heaviest edge and then putting this back. Okay, so that's B. Let's see, what's C asking? C is asking, E is already part of the MST. Have an edge already in the MST will only lower the overall weight of the MST, and so no change is needed. This edge that I have already decided is small enough to be part of the MST just got smaller. So it is still part of my MST, and the overall weight of my MST got smaller. So that does not change the MST at all. And then finally, if E is already part of the MST, but its edge weight has gone up, we need to do an update. So what we're going to do is that we're going to remove E from T to get 2 components, right? Because every single MST is a bridge. Removing a bridge creates adds one additional connected component, right? So now we have 2 components. Because we have 1, now we have 2. We now find the lightest edge across this newly created cut and add it to T to update MST. This is an application of the cut property. It takes O of M to find the lightest edge across the cut. And so the answer is O of M. So we just checked it to see for every edge is a part of one or the other other subset. And if it then the 2 different subsets, we consider it as a candidate edge across this new cut, across this cut, and we find the minimum, and that takes all of them. All right, any questions on 5.22?
For part B, I know this is the correct way to do it, but do you have a rigorous proof that by doing this, you do obtain a MST? Like can you prove that take any other spanning tree, then this weight, total weight, and under this changed weight is smaller than or equal to the other tree?
I think the proof is in the lecture.
Yeah. It's also the cycle property, right? So let's suppose I don't have an algorithm, right? Because there's one thing to do the algorithm to get the fastest thing. It's another thing to just prove, you know. So let's say I add this this newly decreased edge into my MST. What's going to happen? I'm going to create a cycle, right?
Yeah.
Correct. Right. So that's the truth of MSTs and adding an edge to the tree. It's going to create a cycle. And what do we know about the cycle property is that the heaviest edge of a cycle cannot be part of the MST. So once I have created that cycle, if I went in and grabbed the heaviest edge and removed it, I now have an MST. Right?
That property says the heaviest edge cannot lie in some MST, not every MST.
It cannot. No, the heaviest edge of a cycle cannot be in any MST. All MSTs cannot have that heaviest edge in the cycle.
Okay, that's a little bit different from the problem 22. It says then there is a minimum spanning tree that does not. Probably maybe if you have some ties. Maybe if there's another edge on this cycle has the same weight, both are heaviest.
So this is the cycle property as described in Wikipedia. For any cycle C in the graph, if the weight of an edge E of C is larger than any of the individual weights of all other edges in C. So if it is uniquely the largest, the heaviest edge, then this edge cannot belong to an MST. Any MST. It cannot be part of any MST.
Well, as I said, if you have ties, that's not.
I agree. If you have ties, that's right. So in my algorithm, find the heaviest edge along the path. If the heaviest edge is greater than the edge I have, right, then that is now the heaviest edge, and I no longer can use it. But if it's equal to my updated edge, it can stay. That's fine, because you just have to remove one of the edges to break the cycle. So this is saying that if it's not a tie and one of the edges in the MST is now heavier than my updated edge, or the heaviest edge is heavier than my updated edge, it needs to be removed so that I can replace it with my better edge.
So if it must not belong to the MST, you remove it, then how can you justify that the remaining part is a MST?
What? If I remove the heaviest edge?
Yeah.
I don't have to prove it because the much smarter people than me have proven the cycle property. I can just use it because I know it's a property of the MST.
Okay.
Like I don't have to prove to you that the cycle property is true. It's an understood, like someone has already proved it, right? Like we're building on the shoulders of giants that I've already proven
No.
a lot of these.
I know the cycle property is true. Actually, it's a homework problem, so I accept this. My question is, if we accept this cycle property, you remove this heaviest edge from the cycle, and you know that because this heaviest edge cannot is an MST.
If I add an edge that would have created a cycle, and then I remove the heaviest edge, then everything else is an MST. Yes.
Is this some theorem or it's very straightforward?
So you can create an MST in the reverse of how an MST is normally created by starting with a graph and then removing the heaviest edge that's part of the cycle one at a time.
Oh, okay.
That'll get you an MST. Yes.
I see. Okay, thank you.
Yep. All right. Any other questions on 5.22? Okay, cool. Last problem, 5.23. MST with U as leaves. This is an alternative solution to the one I wrote originally, but I like this solution better, so we'll go for that. So sometimes we want light spanning trees with certain special properties. Here's an example. Input an undirected graph, G, with edge weights W's, subset of vertices U and V, output the lightest spanning tree in which the nodes of U are leaves. There might be other leaves in this tree as well. So remember what I told you that a leaf is just anything that's by itself a single is only attached to one other vertex. So basically the ends of your spanning tree. And the answer isn't necessarily going to be a minimum spanning tree. Given algorithm for this problem, which runs in O of E log V time. Hence, when you remove nodes from U from the optimal solution, what is left? But we can give a good solution on this. All right. And this is what I mean by like you should understand how prims and Kruskal's algorithms work internally, even if they basically get you the same answer. We're gonna take the opportunity to use what we know about prim's algorithm. This is how prim's algorithm would continue on this problem. So what we're gonna do is we're gonna remove all the U vertices from V. We're gonna call this modified graph G prime. Now we're gonna run Kruskal's on G prime. Could have been prims, doesn't matter, and get back a partial MST. Okay, we have this partial MST that doesn't include any of the vertices in U. And then for each vertex in U, find the lightest edge that attaches it to the partial MST, making sure never to connect to a vertex that was in U. So basically, we're going to connect all our U vertices back onto this partial MST the same way that prim would. What prim does is it builds this partial MST initially and then grabs the vertices that's not in our subtree and attaches it one at a time back to it using the lightest edges. And so we return this whole MST. What we have to be particularly careful about is that if we already attach a vertex from U into our partial MST, not to consider that as part of something we can attach to. And so what I mean by that is that, like, let's say we have this cluster of partial MSTs, and we have this U vertex that we are going to attach right here. Then my next U vertex can consider being added here, or it can also be considered added here. What I cannot do is add my U vertex here, because now this is no longer a leaf. I have to add it to one of the vertices that was in the original partial MST, never to a U vertex. Okay. Why does this work? Because we seek to get an MST such that all vertices in U are leaves. By removing all vertices in U from G and running Kruskal's, we create a partial MST such that we, when we add vertices U back to it, there will always be leaves. We take care not to attach to another vertex in U, because this would cause that vertex to no longer be a leaf. This works because the cut property allows us to take the lightest edge between U and the partial MST. Now, your question might be, well, what happens if we remove the vertices U and whatever remains of our graph is disconnected and we can't build a partial MST? Well, if that is true, then you could have never done this, because you would have needed a U vertex to be an intermediate vertex within the insides of the MST to begin with, to keep the MST connected. And that's the case, that U vertex could not have been a leaf. So the runtime for this is that removing all vertices in U from G is O of n plus m, running Kruskal's is O of m times log n, adding U back to the partial MST over the lightest edge is O of m. So you consider all the edges, and then you add them back as leaves, and then it takes O of m log n as your final runtime. Any questions?
So the way that we solve this problem, that using the notion of leaf nodes, is when first we're separating them and then create a
Yep.
partial MST, and then
Yep.
when we look at minimum edges between the partial MST and the
Right.
leaf nodes, and we attach them back to the MST, but we not to attach the leaf node in the U to whatever
Right.
the set is.
Yes. Yep.
So are we assuming that because they are leaf nodes and there exists some edges that we can attach them back to the partial MST and then let them remain as a leaf nodes?
Yeah, like this, the solution to this problem assumes that this is even possible. If it's not possible, then you could add an extra check to say, yeah, if it's not possible, then return an error or something. But when the question is asked like this, like I said, an MST problem, typically, if we're asking you to give us an MST that fits these properties, we're not trying to get you to be like, oh, that might not be possible. Like there should be a possible solution to this.
Thank you.
And if there's a possible solution to this, then this algorithm will work. Any other questions?
Step 3, why the running time is OM? I think you are going to use prims here, right?
No. So when you run prims or when you run Quizscalls, you have to sort the edges in some way so that you know which edge to connect, because it means that like if I was to connect two U vertices to each other, I have to consider all the edges that could possibly work. However, because I don't want to connect U vertices to each other, and I only want to connect those vertices to the already existing partial MST, I can isolate what I consider to be available edges down to each individual vertex. So for
you
any
just
point,
scan through the linked list of some vertex and of U. Yeah. Okay, got it.
And you find the lightest edge that is connecting to the partial MST. You don't have to compare to any other edges. They only care about each individual vertex as you go around and figure it out.
Okay, thank you.
Yep. All right, let's take a break. We have one final. Oops. It is currently.
Yay! 7.
Yeah. 6:34. Let's come back about 5 minutes, so about like 6:39ish. All right. Hopefully, I can get through this before 7, and that'd be great. All right, take a break, everybody. I'm back, but I won't start for like another 3 minutes. By the way, MSTs are my favorite graph subtopic. MaxFlow is probably my least favorite. I do not enjoy MaxFlow. I think it's like, I don't know. I find them to be kind of annoying to play with. I think there's just like too many steps to go from like one thing to another when like you could easily explain it to someone, but like to write out the algorithm, there's just like all these like steps you have to write to build. Yeah, these are the last set of problems. I'll probably answer some questions that's in id, but if id asks for additional problems, I'm probably not going to go over it. What's been everybody's favorite part about this class, since I asked the least favorite part earlier?
Office hours. Is that too?
Oh, really?
I think for me, I've actually really enjoyed the homework problems that we don't have to write code for. It's kind of refreshing to not have to like reiterate something that's already given to us in the lecture.
Mm.
I don't think I'm allowed
That's
to be
cool.
that, hand wavy any of the courses through the whole program here.
Yeah, that is true. But I feel like sometimes, I guess like I'm like, oh, I don't know if I need to be a little bit more precise, a little bit more descriptive and detailed about this, or if I can just be like, yeah, this is just kind of a known thing. And it's oftentimes like not even like, easy as a TA either. So like I said, we absolutely like calibrate between the TAs on how we want to grade certain problems, and TAs don't always agree either. We're all human. So sometimes like, some TA will be like, I want a little bit more description about this part of the algorithm, and someone will say, no, it's actually, pretty well understood. We can just let them kind of like state it and move on. And then there's like a fine balance of like, if we do it one TA's way, what is the mean and median score? If we do it the other TA's way, what does that look like? Where do we want to target? So there's a lot of back and forth between the TAs on that too. It's not an exact science, unfortunately. That's how it goes.
That's not the algorithm should be. Algorithm is all about idea. It's not about formatting the way you write things. I think there are too many restrictions in this class. It makes it less interesting.
I mean, it's a design of algorithms, right? Like if you wanted something to be exact, and some students do, then programming that algorithm is very exact, whether your algorithm works or not. Some students hate that, right? Some students want to be a little bit more freeform and describe the algorithm. So then it comes to like when you're at work and you're trying to write a design or a proposal or a requirements, how precise, how exact do you have to be? Some designs are very detailed and gives you everything you need to build up a system. Some designs are not detailed enough, and you have to like, you have to infer certain things. You have to make things up. You have to go look it up and ask questions. I don't think like it's particularly good or bad one or another. Anytime you have a free form solution or answer to something, it's a balance. I don't have it correct. All right? Even like research papers, or why do people have to defend their dissertations? Because it may not have enough detail, or it may not say enough about the problem that they're solving. I don't think it's specific to this class.
I understand that some standard must exist so that maybe the grading becomes easier and maybe we convey the idea clearly. But for example, writing a code, writing some pseudocode would mean a lot of penalty. I don't understand. Does this mean that I don't understand the algorithm?
Well, like, it's a free-form question. So when you go to grade it, there's certain expectations that we have to get enough details to understand what you're doing, right? It's not. I don't think it's objective. I think it is subjective. I think sometimes we do grade on things that a student does find unfair, and then we might adjust it either this semester or next semester. We're not like so arrogant that it's like, okay, it has to have these exact same words in it. In order, like 100%, we're never going to budge from this. I think it's a matter of like, we have a target understanding that we want students to be able to both have and to show. And does your solution show enough understanding? And we have to work with each other on what we think that's appropriate. I guess I'm not saying that you're wrong. I'm just saying that like, it's not an exact science. Even if it's on algorithms, it clearly isn't, and we're trying to get to always trying to improve. And so your feedback is always welcome. All right, let's tackle this last chapter, and hopefully everybody can get some good rest before the exam. So 7.8, 7.18 A and B. What's that look like? 7.18. All right. There are many common variations of the maximum flow problem. Here are 4 of them. There's only 2. The reason why it's only A and B is because C and D are actually linear programming type questions, which we cover later in this class, and not with the max flow. So that's why we're only doing A and B right here. Okay. So part A is that there are many sources and many sinks, and we wish to maximize the total flow from all sources to all sinks. So what's that going to look like? You can imagine that if I had a normal max flow, I have a single sink, and okay, and it doesn't really matter what the capacity is on this. This is just a dry. And so if I had more than one source, what I might have is S1, and then this is S2, and this is T2, and then might have more nodes like that.
We
and so
can't
forth.
see the whiteboard right now.
Oh, silly me. All right, is that better?
Yes.
All right, so my initial drawing just had the S, A, B, and T, and then I added the S2, C, and T2. So this is what a flow network with multiple sources and multiple things would look like. Now, this is important to understand because I told you, right, that like you can make some assumptions about a flow network if I give it to you as this is a flow network. So if I give you a flow network and I say, hey, this is solve for this. But if I specifically alter that and say, this is now a float network with multiple sources and multiple sinks, you can't come back to me and say, oh, I assumed float networks only have one source and one sink. That doesn't work because I've told you explicitly that we're gonna make a variation of the standard. Trick question. Don't ever answer like, oh, this is a trick question. You can only have one source and one sink, and therefore this is an invalid problem. I'm not solving it. Like that, you'll get 0 points for that. When presented with a I say that because I've seen students do that. It's like, we give them like a specifically changed graph, and they're like, graphs don't work like that, and therefore this has no solution, and they just handed that in and got a 0, and that's unfortunate. So don't do that. Let's see. So this is S 7.8. All right. Yeah, that's good. Here. Right. So we're going to create this subset of S that's all the source vertices. And then we're going to create the subset of T that's all our sink vertices. And then we create another graph, a alternative graph such that G prime equals V prime E prime, such that V prime is all the vertices plus S prime and T prime. And then E prime is all the edges plus S prime S. For all S's in S and T. What is this doing? I think I missed a letter here somewhere. Let me see. All right. I think what I meant to say here, give me a second. Let me type it up and add it back into this. A little update here of what that is. All right. We're going to create a super source and a super sink. Okay. And then we are going to all right, so we're going to add this special super source and the super sink. And then we are going to add to the edges an additional edge from the super source to all other sources, and a super sink to all those things. So if we were going to draw it here, it would be something like this. So we add these edges, okay? Let's do this. Okay, so if that's our original graph, we are going to add this special, oops, what the heck? Okay, this super source, and then we're going to add this edge, these edges, okay? And then why can't I just move this? Okay, that's neat. I don't have a move button. All right, and then we're going to create this like little super sink right here. Okay. The reason we want this is that we want to create a float network such that we have one source and one sink. If we don't have one source and one sink, we're kind of like, not really we don't actually have like a flow network that we can really solve, right? And then, so that is our new graph. And then we want to create capacity such that we have the original capacities, and then the capacities of S super source to any of these sources is infinite. So we want this to be infinite, and we want this to be infinite, and we want this to be infinite, and we want this to be infinite. Okay. And then we can run the OMSCS algorithm, and that gives us this solution, which we then take the solution back flow, and then we subtract the flow for all these edges because we don't care about them. Okay. And the reason why we have to do this is infinite is because remember I told you that sources don't have a capacity. The source, these edges have a capacity, right? These edges have some capacity of, let's say, like 1, 2, 3, or whatever. But if I was to put an edge into the source, it has to have infinite capacity because there's no limit to how much capacity can come in here. Alternatively, you can add these two together and put it here. So if you are uncomfortable with the infinity, you can add up how much flow S would have to give to saturate all of its edges coming out. So if S1 can output 1 and 1 plus 2, then you can make this 3, and then you can make this 10. Like if you're uncomfortable with infinity, you can actually assign them values, or you can just make them infinite. It doesn't really matter. Either way, the point is that S2, the output coming out of S2 cannot be constrained by this capacity. And so a 10 here would make this make this unstrained coming to 3 and 7. Okay. So because sources can provide unlimited flow and sinks can receive unlimited flow, we need to represent this in our flow network. To do so, we add a S prime and T prime with unlimited flow so that when running the max flow algorithm, all edges into sources and edges out of sinks are not bottlenecks. Once we have modified max flow F prime, we remove the edges, we add it to F. And so we've basically expanded our flow network so that even though we have multiple sources in one sink, it behaves as if there is one single source and one single sink. Any questions on 7.18a?
When we're working on the max flow variant, when do we suggest adding the S prime and T prime so that we have a single sink and single source? When do we need to add a backward edge from T prime to S prime? Or we only have to do that when we're doing feasibility?
I think that's a different problem. I don't think you need it here.
Okay, thank you.
Any other questions?
When we solve maximum flow problem, do we tend to use this Edmond-Karp algorithm instead of the Ford-Fulkerson algorithm because the runtime is better?
No, I use Edmond-Karp's because I have no idea what the capacity is. If I use Ford-Fulkerson and someone then goes, oh, by the way, those capacities are not integers, then I'm kind of screwed, right?
Oh,
so
okay.
Like unless I'm told that the capacities are integers, I'm just going to use the more generalized solution.
There's no way we can estimate the capacity in advance, right? So I think we always should prefer the Edmond-Karp.
There are certain problems that if I told you I have integer capacities, it is better to run Ford-Fulkerson because it does something like different. So for example,
they are just the same algorithm except that, oh no, Edmond-Karp is just a special case of Fulkerson, right?
It's a more specific case of for Fulkerson. Yeah.
And Emmett Carp used BFS when exploring the ST path, and
Yes.
for Fulkerson use either.
It can use any pathfinding algorithm. So first of all, DFS and BFS are not the only two pathfinding algorithms out there, right? Like you could in theory run full Fulkerson with dice rest. That works. It just has not a great runtime. You could also use a better specialized pathfinding algorithm. And I do believe there are some variants of full Fulkerson that's actually better, faster than Emmons Carp because of that. We don't cover it in this class, so don't worry about it. But someone else has their hands up. Christopher, do you have a question?
Oh, sorry, I must have accidentally hit the button.
Oh, no, that's wrong. Okay. So moving on to part B. Part B asks, each vertex also has a capacity on the maximum float that can enter it. Okay. So part B, where are you? And again, I'll post the solution and then I'll draw it up so that we can talk about it. So basically, what this kind of looks like is that A also has a capacity. So if I said that capacity of this node is 5, even though the incoming edge has capacity 10 and the outgoing edge has capacity 10, because A can only take in the capacity of 5, this ends up being a max flow of 5. Okay, because A as a node also has a capacity constraint. So our solution, I want to kind of get that within frame. Excuse me. So let's see C of UV be the capacity of the edge UV. So SA would be 10, right? And a C of V is the capacity of vertex V. So if C of just A would be 5 here, we create a new graph such that we have the source plus V in for all vertices of V, and V out for all vertices of V. And notice how I say not including S. That means that because source is not going to have, source does not have a capacity. It doesn't make sense for source to be included in this list of vertices that I want to create this in and out of. Okay. Because S is unbounded, right? And then for E, I want to create a new edge of V in and V out for every vertex except for the source vertex. And then I also want for every edge UV, I want to create this new V out and V in. So I want to connect an additional I want to change the name of this UV edge to U out and V in. Yeah, V/S is the same as V minus S. That's the same thing. Yep. And then so we want to create this capacity where everywhere that I had this vertex, I want to create this V in, V out, and everywhere where I have a normal edge, I want to create this U out, V in, and then we run the image carve algorithm, and then we return a solution of our flow by subtracting all the extra edge flows that we have. And the reason why we do this, right, is that when you add to the graph that you are going to run into image carve, your output is going to have all these extra edges that you've added. There is a flow for every edge that is in your capacity edge list that you run in image carve. But when we return it, it doesn't make sense, right? Because this V in, V out, or flow of V in, V out has no meaning to the original graph. There is no V in and V out in the original graph, right? So you have to remove it from your flow answer. Otherwise, you just have these like extra data that doesn't make any sense to it. And so what this ends up looking like is that if we go back up to our, this little diagram here, is that we, instead of, actually, I might just draw it alongside it. Okay. So instead of what we have originally, we're going to change this to S to oh yeah, and this could potentially also have a because T is a vertex that you're entering. It could also potentially have a capacity. So T. Okay, so we've taken this initial input that has a capacity on the A and T, which makes no sense for a normal max flow algorithm, and we've spread it out, and we've taken this A and we split it into A in and A out, and we added a capacity of 5 to its edge. We've taken this T and we split it into T in and T out, and we've given the capacity of this 7. And notice how originally I have a edge from A to T. A to T in this new graph or new flow network makes no sense. So I changed that from A to T to A out T in, and that's what this part right here means, is that if I had an edge UV, I change it to U out and V in, because I now need to be able to connect to the A out from what I did with this vertex, which is, yeah, so right here, U, V in and V out for each vertex, okay? And so now when we run that through to get our flow, this part right here, I'm just gonna convert it back, right? So where I have U out and V in, I convert it back to the original edge, and I get rid of all of these extra edges that I created. All right, so then the correctness is that we update our G to add additional vertices and edges, which represent the capacity of each vertex. In order for the vertex capacity to be constrained, there is an edge from V in to V out, such that the edge constraint C capacity of V in, V out cannot be exceeded. This allows us to run the max flow algorithm as is. Once we have our modified max flow F prime, we remove the edges we added to get F. We also replace U out V in with the expected FUV for all edges in E. Runtime to create the graph is O of n plus m. To update or add to the capacity is also O of n plus m, and the mx carves is O of nm squared. The reason we use mx carve is because I have no idea if these capacities are integers or not. And then to remove the extra edges between vertices and replacing them is O of n plus m. So our overall runtime is dominated by the O of n m squared. Okay. Anybody have questions about the solution?
I just had a general question, not for this question, but are we allowed to use sorry, the residual graph as a black box? I read it somewhere. I just wanted to confirm.
Yeah, you can say something like create a residual graph, and that can be a black box in what you're doing. Yeah, and I actually showed that in 7.19, so I'm gonna move right on to 7.19, which will demonstrate that. Any other questions before I go?
So the residual network can be used for solve B?
I don't know. You don't. Well, the residual network doesn't do anything for part B. I think he was asking, like, just in general, can I use a build a residual network as a black box? And I said yes, and I will demonstrate that on the next problem. I don't think he was asking a question related to this specifically.
Yeah, that's correct.
Okay, so
All right.
B different from A is because we added capacity, and then
we added capacity to the vertices, which is different from what a normal Maxwell problem would be.
Okay, thank you.
All right. 7.19. All right. Suppose someone presents you with a solution to a Maxwell problem on some network. Give a linear time algorithm to determine whether the solution has indeed a max flow. So the way this is asked, what you want to do, right, is you think, well, how do I know that a max flow is valid? Well, a max flow algorithm terminates when there's no more path to be found from S to T. That's how you know that the max flow algorithm can no longer find you a better flow. It has terminated. So if we can verify that terminating step, then we have effectively verified that our max flow is in fact a max flow. Okay. And the way to do that is that we just basically run the steps at the end of one of these algorithms. It doesn't. I think we have to. Yeah. Don't remember which algorithm I used. I ran Explore, but I guess you could have done BFS or DFS, or it doesn't really matter. All right. So first, okay. So the other thing is that this person might be handing you a bunch of junk numbers. So we have to verify all parts of it. We don't trust this person. We want to say, you know, let me double check your work. Okay. So first of all, you have to verify your edge capacity constraints. So you don't break any of your edge capacities. For every flow that's given to you on this supposed max flow, we check that the flow is actually under our capacity, that we didn't go over. Okay. So that's one. We have to verify the flow in and out of V is conserved, right? So that's the other thing that max flows do, is that the flow coming into A and leaving A are exactly the same. Otherwise, you don't have a conservation of flow. So these are the properties of a max flow. So for every vertex in V minus ST, because those don't actually have a constraint because they're not actual vertices in our flow network other than the beginning end. We verified that the summation of all the flow coming into V is equal to the summation of all the flow leaving V. Okay, that's what this represents. So that's our conservation of flow. That's our second thing to check. And then verify that the flow out of S and into T is conserved. Okay, so the summation of all the flow coming out of S is equal to the summation of all the flow coming to T. Okay, the source and our our sink must match in terms of how much flow is going in and out, coming out and going in. Okay, so once we have that, we are going to actually verify if F is indeed a maximum flow. And so to do that, we create a residual network. You can use this as a black box. Just say take this and create a residual network. Okay, and then we get back our residual flow network. So this GFF, V, EFF, CFS. This is the parts to our residual flow network. Then we run explore. We run explore to verify that we cannot on S to verify that we have no additional path to T. If we have an additional path to T, that means we can send more flow from S to T. If we don't have a path from S to T, that means that there's no more flow that we can send from S to T. This is the definition of what a residual network gives you. So the correctness is that steps 1 through 3 verify each property of a valid flow. This should be in your lecture, should be in your textbook, what the properties of a valid flow is. And then step 4 verifies the max flow by making sure that the residual network has no path from S to T. And that's by definition of what a residual network and path does. And so the runtime is that verify edge capacity is O of n plus m. Verify the flow into and out of V is conserved is O of n. Is that right? It seems like it should be O of n plus m, right? Because it's a summation. Let me see. Step 2. Yeah, it's a summation. So that should be O of n plus m. Let me update that runtime. Give me a second. Because you have to check all the different edges. O of n plus m.
Why part A is m plus m? I think part A is just m.
Part m.
Each edge capacity. But it doesn't matter. It will be sub.
Yeah, it can be all of them. That's fine. That's fine. We can go with all of them. Update what I have. All right. So verify edge capacity constraints are met is O of m. Verify into and out of V is conserved for all of them, O of n plus m. And then flow out of S and into T is conserved. Is this O of n plus m? This one should be O of m though, because I only have 2 vertices that I'm checking. So that's it.
But you need to sum up, but the number of nodes won't exceed n.
Right. Yeah. Like if
I
have 5 edges coming out of S, I only care about each of those edges. I don't care about how many vertices are in between S and T.
Can we be a little bit sloppy regarding this, because it doesn't matter. Eventually, you are going to absorb n into m. So if I write everything as m plus n, is that okay?
I think it's generally okay, because as long as it's I generally use O of n plus m when I'm dealing with like the full graph. So I think it'll be okay. But if you can be more accurate than not, then it's also always good to be more accurate than not.
Why do we need to check step 3? I think if we check step 2, then step 3 is automatically satisfied.
Step 2. So flow in and flow out.
There's nowhere this flow can go but to go to the sink.
Let me think. So if all my intermediate nodes are correct, does that automatically imply that my source is giving the same output as my sink?
I think that isn't it the true that the conserved flow in flow out does not apply to sink and source?
Yeah, but his comment is that like if I've already conserved all the flow within the flow network itself, does that automatically imply that source and sink are also matched up? I'm thinking. It should. I think it should, but at the same time, I'm gonna keep this in there just for completion's sake, because it's actually, I think the lecture covers this as like the three properties of a valid flow, and so I would verify all three properties because that's how I would approach the problem, rather than say like verifying property 3 implies verifying. I mean, verifying property 2 implies verifying property 3. That to me seems like a too indirect of a way, and I would just rather just go and verify each step.
You can prove this rigorously. You can just sum up all the inflow on the left and sum up all the outflow on the right.
Right.
Then you will cancel those intermediate nodes, and what is left on the left is the inflow of the sink, and what is left on the right is the outflow of the source.
Yeah, I don't contradict that. I just think that if I'm giving three properties of a valid flow, I'm going to give an answer that verifies all three. To me, I'm going to verify all three properties. I think that's just the easiest way for me to answer a problem. But you're welcome to not do that and then prove it. Right? Like either you prove each property, or you prove it in your correctness that doing one implies both, and you're gonna have to write that eventually, right? Like you're given the three properties of a God.
The textbook only have 2.
The textbook only has 2. Oh, okay.
Yeah.
That could also be true. In that case, then sure. Let's see. Why would max flow not? When right past it. 7. Linear programming. What page is this on? Does anybody know? Oh, flow. Okay, 7.2. Oh, okay. Yeah, then sure. You can leave it up. That's fine. All right. Anybody have any other questions on this problem?
Do we need to include the runtime of constructing the residual network?
You should. Although kind of included all in one place. Yeah, I kind of put it all in one time. But I guess You should, but I put it all in one step. So my step 4 is verify f is in O of n plus m. But I would be safe to write down the individual parts of that step into one runtime. It is not O of C m because I used because it's O of n plus m because I'm just running explore. All I'm doing is verifying if there's a path. I'm not running the for focusing over and over again to with the subroutine of for focusing over and over again to find the max flow. I'm just verifying if there's a max flow or not, and that can be done O of n plus m with explore. All right. Any other questions?
Wait, I think you need to simplify the answer to OM, right? Because it's connected.
Right. You can, but you don't have to.
Okay.
The runtime for the residual network is n plus m.
Yeah, because you're just building out the graph based on the information that you have.
Thank you.
Okay. All right. Let's see. 7.21. This might actually now be my longest office hours. I guess that kind of makes sense.
Yay, we make a record.
There was like 1 billion questions. All right, 7.21. Critical edge. All right, I'm gonna just speed it up by posting the entire solution and question at the same time and just going over it so that we can try to maybe finish in about 7 minutes. Oops. All right, 7.21. An edge of a float network is called critical if decreasing the capacity of this edge results in a decrease in the maximum flow, given the efficient algorithm that finds a critical edge in the network. So what I'm going to do is I'm going to run Edmund's cart to get back my maximum flow. And then I'm going to create a residual network with said flow and get back my residual network. And then for each edge such that my flow is equal to capacity, because these are going to be my saturated edges, right? If you decrease the flow of a non-saturated edge, it doesn't matter because it didn't actually need that edge to be critical, right? So I'm going to take all the flow that equals my capacity, and then I'm going to run explore on G from U and see if V is reachable, which means that if I have a way to go from U to V from a different path, then it is not a critical edge. If you cannot reach V, that means that it is an edge that if I decreased it, I wouldn't be able to redirect that flow to anywhere else because there's no path. Then therefore it is part of my critical edge. So we return this list of critical edge. So the correctness is that the residual graph is built after the max flow is found. If an edge is at capacity, which is flow equals capacity, then it is a candidate for a critical edge. If it's not at capacity, we could reduce its flow and still be at max flow, right? Because that makes sense. For each candidate, we see if there's still a path from U to V. If there is, then we could avoid using UV and still push flow from U to V because there's already an additional path. If this is true, we can decrease the flow of U to V and that flow to the path that we have found because there's still a path. So UV is not a critical edge, otherwise it is. And so the runtime is MN's carb, residual graph, residual network, and then for each edge, run explore O m plus O n times m equals O n m plus m squared, which reduces to O n m squared, which is the runtime of MN's card. Right, yeah. Any questions?
I'm thinking of another way. I don't know whether it's correct or not. Because the maximum flow corresponds to the min cut. So you first run this algorithm to find the min cut. Then I claim that any edge from the S component to T's component would be a critical edge. Because if you reduce any of them, then since this is a min cut, then the min cut would be reduced.
How would you find the min cut?
I will run either Edmond Carp or focus and then
Okay, so
I find the residual graph and then I find the nodes reachable from S.
Right. So the problem with that is that a single graph can have multiple min cuts, and you would not be able to find that using that approach. So let's say we have, which is actually good to know that you can have multiple min cuts, right? So if I have S, oops, that's not okay. So if I have S to A, and this is 10, and then A to B, and this is 10, and B to T, and this is 10, right? Each of these are actually critical edges, right? If I decrease any one of these, I would decrease my overall flow, right? When you finish this and get the residual graph, and you try to get the min cut, you end up not seeing all the min cuts after S, right? So each of these, this is a min cut, this is a min cut, this is a min cut. It's actually 3 separate min cuts that indicate 3 separate critical edges. And while it is true that finding all the min cuts finds you all the critical edges, there's no like simple algorithm, that would just be like, okay, well, how find all the min cuts in my graph. Does that make sense?
To his point, technically, I think 721 only asks for a critical edge. So if you just wanted to find one critical edge, I think that approach would work. But if you wanted to find all of them, then it wouldn't.
Sure.
Just,
if you're looking for one critical edge, yeah, that's fine. That's fine. Okay, I didn't read it. I did not realize that finds a critical edge. Yes. Okay. If you just wanted to find a critical edge, any edge across a min cut would in fact be a critical edge. Yes. Okay. All right. Next question. 7.22 is update edge capacity. Right. In a particular network G, whose edges have integer capacities, we have already found the maximum flow F from node S to T. However, we now find out that one of the capacity values we used was wrong. For edge UV, we used CUV, whereas it should have been CUV minus 1. This is unfortunate because a float uses the particular edge at full capacity. We could redo the flow computation from scratch, but there's a faster way. Show how a new optimal flow can be computed in O n plus m time. Okay, so step 1, create a residual network. Step 2, find a path in G from U to S with explore. From U to S. update the flow along this path by -1. Find the path in GFF from T to V with Explorer. Update the flow along this path by -1. Decrease the flow of and capacity of UV by on the updated capacity and add outputted flow to the updated flows and return it. Okay. So what I'm going to do is I'm going to reverse my very final step of forward focusing, which is the reverse of how I found that final step of forward focusing, right? So if I had created, if I found a path from S to T, and I consumed that path by updating one single capacity, that means that my residual network will show the back, show the back edge to that as having capacity. So that means I can find a path from T to V and from U to S on the back edge. And if I can do that, I can decrease all of that flow by 1 so that I can update my flow from V to U by 1 and get myself back to a appropriate flow. Now the question is, had I not used this edge UV, would I have found that one additional flow somewhere else? And what we can do is run forward focusing on this updated capacity and add that updated flow to the updated flows to the other flows and return it. And the reason we can do that is because we know that forward focusing runs on in O of MC, where C is the capacity. By reducing the capacity by 1, we know we are guaranteed to only run one more run of forward focusing to get the final capacity, if that final capacity is in fact one more. So we revert the final round of forward focusing by finding a path from U to S and T to V using packages and decreasing the flow by 1 so that we do not oversaturate. So that's what we have done. We have oversaturated E. So we're going to decrease that all from V to T. We then take all the updated values and run one more round of forward focusing. We know that we can at most decrease our total capacity by -1. And so we need no more than one more round of forward focusing to get our total capacity. So creating the residual networks of M and running explore twice to figure out where we are is O of M, and then running, I have other parts that I did not paste. Okay. Where are we? Okay. Cut off. Updating the flow on the path is also O of M, and then running one more round of forward focusing is O of MC with C equals 1, which makes it equal to O of M, and so your final runtime is just a whole bunch of O of M's, which comes to O of M. Any questions about this?
Could you just zoom out real quick so we can see the whole thing? Sorry.
Yeah.
Thank you.
Cool. Yep. No problem.
Is it possible that you can, I know if initially when you use this UV edge, there exists a path from S to U, U to V, and V to T. Now, I mean, if you go if you do further augmentation to the path, then is it possible that eventually you cannot find a reverse path from T to V and U to S?
Edge UV. I know I have sent flow to V, then flow from V to U, and then from U to T. I know this because VU is saturated. And so I know based on that the back edges must have flow, because the only way I can send flow forward is to update the back edges with additional flow.
Okay.
Maybe I missed it, or maybe it's a typo. But what would step 5 be?
Step 5. Oh, it's a typo.
Oh, love to hear that. Thank you.
So 1, 2, 3, 4, 5, 6. Okay, I've updated my notes. All right, any more questions?
Just for clarification, when we said a edge is saturated, is it how we say it? That means the flow is same as capacity, right?
Yes.
Okay.
Saturated. It's at capacity.
Okay. The flow is same as capacity.
Mm-hmm.
Okay. Thank you.
All right, I am going to check on it and see if there's any questions.
Are you going to
Hopefully
solve the
there's-
last one?
The last one, what was the last one?
The hard one?
7.24. I don't think I'm going to. I don't think I had the. I don't think I had the answer to this. I did not. I don't have an answer to this. I could probably work it out later and see if I can post it, but I do not have a prepared answer for this.
Just for clarification, for the previous question, is it possible that the flow does not decrease even if you decrease the capacity of that edge?
It can. So either I could have used a different path to go back to +1, or that edge was actually a critical edge, and decreasing it by 1 decreases my flow by 1.
Okay, thanks.
I got a question. How do you ascertain that running one round Ford Fulkerson is only M1 or OM?
Yeah, let me go back to what I had. All right, so because I know that I decreased my capacity by 1, my capacity, wait, this is a quiz thing, Joves? What am I doing now? Okay. I am not going to answer that question because it's a quiz thing. I'm sorry. Thank you for letting me know.
I have a quick question on the runtime of this question. So, why does running explore twice? Why is it only O of M and not N plus M?
So yeah, because this is a float network problem, we know that there is at least M equals N. M is greater than or equal to N minus 1, so we can just replace all of the N plus M runtime with all of M.
Okay, gotcha. Thank you.
You also don't have to. Like if you don't and you put in O of N plus M, that's also okay.
Okay, cool.
Other questions?
Are you able to clarify some statement in the quiz?
No, I'm not like participating really as a TA this semester, so I don't really want to like go into like the homeworks with the quizzes and answer questions. If you have a question about the quiz, I'm sure you can ask it in like Ed or either privately if it doesn't give away, if it's specific, or once like the quiz solutions come out, maybe talk about it then.
Okay, thank you.
Bill?
Yes, I'm sorry. Just step 7 again. I would just like to understand OM on that.
Step 7. Let me see.
So basically, one iteration of Ford Fulkerson is OM. Is that pretty much what it sums up to?
Yeah, one single run of the Ford Fulkerson subroutine is OM.
Thank you.
Yep. All right. Moving on to Ed to see what questions I might have missed. A bunch of practice problems, which I went over. Go over the question that Dr. Research is. Okay, yeah, I did that. Can you go over homework 5 solution? Jamie has said that it would be done in office hours, so I suggest going there. Question about homework 5 practice problem 3.3. How you find two sinks, source, and intermediate changeable nodes. Yep, you can find all sinks. So I did this on one of the problems, right? I showed you how to find all the sources. All the sinks is even easier. You just look at every vertex in your metagraph, and any vertex that doesn't have an outgoing edge is a sink. So that's how you do it. Looking for interchangeable nodes. Do I need to look for each pair of nodes, check whether they have edges? It'll take. So I think I did that on one of the solutions where I walked from source to sink, and I decided if I have an edge from each vertex, adjacent vertex, then it would have a unique topological sort. And if it has a unique topological sort, then there's no interchangeable vertices. Yeah, so that's answers that. Thanks for doing this again. Your last marathon session was huge help. Yes, thank you. Appreciate it. Thank you. Is there a recording of the session flowing around? And you'll answer that. 5.2, I don't quite understand. What is the relevance of perfect matching and feedback edge set? So I think in the one of the PDFs, like these two problems are kind of combined together by some accident. I always took 5.2 as the feedback edge set, so I answered that. They don't have anything to do with each other. Love I show how to identify problems as one kind and what changes for setting up the problem and solving it. Two things I'm missing: how to deal with tricky problems and how to test my solution in a practical amount of time. Drawing many graphs takes a lot of time, and thinking of good graphs to test it sufficiently is also something I understand. So I came up with some of the graphs. What I normally do is I create like this little diamond pattern that gives me a complete graph with a whole bunch of edges that, enough. I also create a straight graph from S to A to B to T. That's like my go-to graph of like, I just need something simple to figure out. And I also showed one of like, I make a little square and then I make two lines that are disconnected. That's my go-to disconnected graph. So if I feel comfortable that my solution answers all these different small graphs, I'm pretty comfortable with it. In general, I think like a bigger graph doesn't really help more than say a bunch of little graphs. So that's my suggestion. I guess I say tricky problems are those that make us think beyond what we've seen before, presumably to show mastery rather than memorization. I would think that all problems should be fit into that category. I don't like any problems that you could just memorize one solution to and be able to answer it directly on the exam. So I would say that if one of those problems came up, so what happens is that Dr. Brito comes up with an exam, and then all the head TAs take a look at it. And since the head TAs, and again, I'm not participating in this because I'm not TAing really this semester, the head TAs have a good pulse on how the class is doing. So they will oftentimes be like, okay, I think this problem is too similar to the homework problem, and therefore students are just going to regurgitate the homework solution and get 90% of the points, and that makes for a bad problem to test understanding. On the other hand, if they see a problem that's like, yeah, we didn't cover any of the approaches to this problem properly, students are going to have no idea how to solve this problem, and they're just going to fail it. That also makes for a really bad problem. So I think a very good exam problem are ones that, keeps in mind what are the practice problems and what the homework problems you've looked at, and that you need to make a small leap, but it doesn't have to be a huge leap of faith to figure out what that solution looks like. Maybe this question is too vague, but I'm finally getting to where I can solve the book problems. That's good. On my own without looking up too much. That's good. Or can understand what other people are saying in their forums or OH if I really get stuck. However, when something comes up that doesn't fit in the patterns I know or problems I've seen, I don't reliably get a good approach. All I can say is keep practicing. The exam problems are designed to look and feel like the homework or practice problems that you've seen without being like like an exact copy of it. So I would say that if a student told me and they felt honest about it, that they could solve most of the problems that I've gone over today, I would say, on your own without having to look up the solution, I would say you're well prepared for the exam. And if you are not able to solve these problems on your own, I would say you are not well prepared for the exam. And that's not to say that you have to be able to solve every single problem. Some of these problems are certainly more difficult than you would expect on the exam. Get a good feel for that and focus on the ones that you think are fair. And I think you get more and more of that as the semester goes on and you see more of the exam problems compared to your homework and practice problems. I have some questions about topological sorting STCs. If I have a DAG, is it true that its strongly connected components consist only of each vertex in isolation? What does IOW stand for?
Sorry, I was just saying this. I'm pretty
in other words, this is a quiz question?
I'm pretty sure there's a part of the quiz that's pretty much directly that question.
All right, let me skip it. Thank you. Thank you so much, students that are keeping me honest. I really appreciate it. I don't want to be fired in a semester I'm not technically working. That would be awful. All right. I'm going to skip this question in general until I actually see what the quiz is. 3A, can this be done with a black box DFS? I agree, 3.7 deserves a discussion. I went over 3.7, so discussion done. Where's the link to the video recording meeting? Yep. I have a question for office hour. The cut property, okay, Prims and Crisscross and MaxFlow, is not clear to me. Oh, so first of all, the cut property and mint cut MaxFlow are not the same cut property. They're like slightly different, so they're not like exactly related. So keep that in mind. So far understood is the below screenshot. This style is very clear with math on place representing a source and sing. Right, I don't see a specific question being asked. And so that Tim follows up with, you have a specific question about this. But not easy to understand. One lecture asked to. Okay. I don't see a question mark in these two posts, so I don't actually know what the question is. If you want to rephrase what you're what you're saying into the form of a question, I will try to go back into the office hour thread and answer them, but I don't see like what a question I'm trying to answer would be. Oh gosh, what are these? Did I go over these? Am I missing any of this? I'm gonna assume my answer.
I think that's the subset of Dr.
Okay.
Brito's favorites.
Okay, can you please go over 4.12? Did I go over 4.12? I did go over 4.12, so we are good. And please talk through this discussion bottleneckages. I'm confused. Homework 6 bottleneck. What was homework 6? I don't know which question this is. 7.17.
Yeah, what Rohan said for it's homework 6 is similar to 4.20, which is you add a road to a network of roads that reduces the distance or the max flow or something to that effect.
Okay, I'm not sure what this question. Can you please talk through this discussion for bottleneckages? I'm confused. What? So I clicked on that, and let me just make sure that this is not a trick and that was 7.17 was asked. So you're trying to ask, go over 7.17. All right, let me see if I can get back to that. All right, for 3.16 is it correct to imagine the direct. Yeah, you should consider it disconnected because not all classes are gonna flow into each other. Like if you had to take a bunch of humanities classes and a whole bunch of CS classes, they're not gonna have any share any prerequisites. 3.24 says the input is a DAG, and we look for a path that touches every vertex. Okay, is this then asking if the DAG is connected? Wouldn't this be equivalent to finding unique topological sort? I think it is. Yeah, so yeah, unique topological sort is a similar problem. And I gave a solution to that, so you should be set. Could you please cover these two cases as well using black box arguments? Given an undirected graph, the contains a cycle of length k. Given a directed graph, determine if G contains a cycle of length k. So this one, the undirected graph, is NP hard, NP complete. So I'm not going to solve that for you. A directed graph, if G contains a cycle of length k, all you have to do is get the strongly connected components, right? And then see if any of those strongly connected components are of length k, because they can all reach each other. Anything that's in the strongly connected component is a cycle inside of itself. So the size of that strongly connected component tells you what the size of the cycle. Oh no, it doesn't, because yeah, I think so, right? It just because everything can reach inside of it, and then so whatever the size is, you can just create that big cycle. I think, yeah, that's what I'm going to go with. And then anything outside of that is not a cycle, right? Because of the way SACs are, because it's a DAG. Okay. Whew. If you have any cut, I don't know necessarily it is the min cut that matches some flow. I don't necessarily know if it's the max flow. Do we know that these are necessarily the min cut and max flow just because they match? So if the capacities of your cut matches the flow, that means you cannot send any more flow through that cut. And that would mean, yes, that cut is saturated. And if that cut is saturated, then it is certainly a max flow min cut. Yes, because the maximum flow has to be less than or equal to the main cut. So if it's equal, then it is, yeah, I think so. I think if I understand what you're saying is that if you have some cut that matches the flow that's flowing through that cut, is that a min cut? And the answer is yes, because you can't add more flow to it because it's already matched the capacity. Could you explain why the lecture's Floyd-Warshall has a 3-dimensional table, but the Wikipedia entry for Floyd-Warshall uses a 2-dimensional table? How would I translate a solution using a 2D table to a 3D table? What does the Wikipedia look like for Floyd-Warshall? And what this will look like. I'm not gonna lie, guys. I'm starting to fade. Let's see what this table looks like. It doesn't even have a table. All right. So the Floyd-Warshall, does it have a table? Just, oh yeah, it does. Okay. K minus 1. K I J K K minus 1. Goes this. Oh, because no, it's not a 2D table, right? If you look at what Wikipedia does, this is k equals 0, and this is k equals 1, and k equals 2. So you imagine that this is just how they display it. This is a 2D table, but this is on top of this, and this is on top of that, and this is on top of that, and therefore it's a 3D table, right? You just take a cube and you cut it into squares so that you can easily read it, but this is in fact a 3D table. Okay. Sometimes available. Thank you, Tim. Could you cover how to identify the source and sinks in SCCs in a given directed graph after running SCC algorithm? I did that already. Can we go over SCC and reverse of a graph, please, for a directed graph? G denote by.
You can skip that if you want.
Okay. Actual problem. I don't want to walk through a max flow. I think that's something that you can present, and then the students, you can work it out with the students. This isn't a practice problem. This is basically like what does a max flow algorithm looks like, and I think that's really, really good practice for yourself. So I. Is it okay to do DFS and try to find the depth of the graph to know the number of semesters? If not, so DFS, you can't control the path that it takes. And once it finds a path, it doesn't try to find another path. And because of that, you're not going to find the longest path. So you need to actually get the longest path. So that's just doing a DFS on that isn't enough. You have to do some way of finding the longest path. I presented one approach to it. There could be others, but just a straight DFS does not get you either the shortest or longest path. And that is all the questions from that. So general exam tips. These are exactly the same as my exam 1 tips. Nothing has changed for you. You now know what exam 1 looks like. You now have a good idea of what exam 2, not the content, but you know what the timing, what the way the questions are presented are going to be. So any mistakes you made in exam 1, make sure you don't repeat them in exam 2. Anything that helped you in exam 1, make sure you carry that over in exam 2. If you were super relaxed for exam 2, figure out what you did in exam 1 to do it. If you were super anxious or upset about exam 1, figure out how not to do that for exam 2. Your mental state has everything to do with how well you will do on the exam, on top of the preparations that you've already done. Make sure you rest before the exam. Try to be relaxed, slow down, read the problem. Read the problem carefully, read it over and over again, especially on graph problems. Everything about the graph that you are going to use, such as the properties, is it direct or undirected? Are the edge weights positive? Are they negative? Are they is the graph connected or not? All these things matter. So make sure you carefully read what that graph is. I like to write it down in bullet points. Like if I'm told my graph is undirected, I put a bullet point down of saying on my paper that it's undirected. If it says that the weights are positive, I put down the bullet point that says weights are positive. And then once I have written that down, I go back to it, I look at it, and I go, which algorithms even work on this, right? Sorry. My kids are excited about something or fighting. I don't know. If the graph is undirected, you're not going to care about SECs, right? If the graph is if directed, you might care about SEC, but you won't care about an MST, right? If the graph is unweighted, you're not going to care about MST. You can start eliminating black boxes. I would start by eliminating all the black boxes. Like you'll get a list of the black boxes that is available to you. Eliminate all the ones that doesn't make any sense for the graph properties. And then from there, focus on which algorithms you might need. Okay, that's how you start. Read the problem, read it again and again. Same thing with the multiple choice questions. Write down your multiple choice question answers, because remember, you get to go over them with your fellow students at the end of the exam. And if you don't write down which one you answered and you just wrote A, B, C, or D, those are randomized and you won't know whether you had a good outcome or not. So, and that to me is torture. I'd rather know I did well or not, rather than not know at all until exam grades are released. Don't just select the right multiple choice question answer, eliminate the wrong ones. That's super important. Some of those are going to look somewhat similar. Consider through them. The other thing, especially about graph questions, is that some of them might contradict each other, especially MST. If I told you that, the heaviest edge is also always included in the MST, the heaviest edge is never included in MST. Those two are contradictions, and you're going to want one over the other. So you should always read all the answers, because they will give you a clue. The other thing that I like to do is, even if I think I know the answer to all the multiple choice questions, I will read all of them, because, like I said, if there are two MST multiple choice questions, one of them might help you eliminate answers on the other one, right? All these graph questions are somewhat related, and if you consider one question, you might be able to figure out the answer to another question that you otherwise wouldn't know. Okay. And again, I like to answer the MCQs first. You don't have to do that. Some students prefer doing it the other way. It's completely up to you. I just do it this way because it gives me time to know. It lets me know how much time I have on the written problem, so I know how to be how detailed I should be in order to get them all done. If I have like 2 hours left after doing the multiple choice questions, I have a lot of time to really focus, really think about how I want to answer this. If I have a half an hour left, I might, try to get the best answer I can and try to write as much as I can before my time is up. So that's how I like to do it. And then try to enjoy the exam. I like graphs. I actually, when I first started this class, I really hated graph problems. I just didn't I couldn't make sense of them. But after a while, I really enjoyed graphs. I think my favorite topic in the class is the MP Complete, which is the next topic, followed by graphs. Whereas when I first came into this class, I think graphs was my least favorite. Who knows? Maybe you'll enjoy the exam. Hope you do. That's all.
Is it possible for you to share the graph, the little graph that you do to try out problems?
I think I did, but I'll draw them again.
Okay, thank you.
And again, these aren't the only graphs that you should draw, and don't assume that just because these are the ones I use that they'll solve for it. So I have this little diamond one that I like to use. Right, so that kind of gives me my little connectivity. And if you have to make this directed, make them interesting directed in such a way, just to kind of see what would happen if you run your algorithm through this graph. Then if you have to put weights on it, put some repeats, put some non-repeats. Yeah. Like make it like somewhat interesting that it would catch edge cases, but also not so interesting that it becomes super complicated for you to walk through. So that's one of my graphs. I also like to use this one. Just simple graph that what happens if I run this through my algorithm? Does it actually pick? Does it continue? Like that one. So like this one. This kind of this kind of works out like what my any sort of disconnect. What happens if my graph is disconnected? Like if this is not an MST problems and I need my algorithm to work on disconnected graphs. I have my little 4 that creates a cycle. I have my 2 that is out by itself, and then I have my little island. I like to use that one. DAGs are easy. I don't actually have like a specific DAG that I use. I just start by writing a bunch of letters. Oops. And then I just go back here and start drawing like, random arrows and see what happens with my DAG. As long as it's a proper DAG, you should be okay. But I just I don't have a rhyme or reason. Like whenever you see me draw a DAG, whenever I'm using it for a problem, it probably looks pretty random. And then I feel like this covers like most of the problems you're gonna have. To me, these have been sufficient. But you don't have to use mine. Draw whatever makes you comfortable. Draw. If you're a naive kid like me, you can use this in the super S. that cool S that you used to draw in school, in the elementary school. That's actually not a proper graph. Don't use that one, but something like that, something silly. It's up to you. Any other questions? Any other things you wanna me to talk about before we go?
Thank you.
You're welcome. All right. I hope you guys all absolutely wreck this exam and ace it and mess up the curve. We don't have a curve, but you know what I mean. Just go and do the best you can. Okay. Good luck, everybody. Have a good night.
Thank you.
Hey.
You too. Bye.
Bye.